Now, let's talk about some of the salient features of this collective risk model, which is generally developed for a short-term insurance policies. Now, we know when we are talking about the aggregate claims, we have modeled it as the summation of n number of individual claim amounts, and this n itself is a random number, right? So n random number of claims, and for each claim xi being the claim amount for that ith claim. So this is what we have typically thought of modeling for the short term insurance claims, for the short term insurance claims. Now, and here we are more and more interested in finding out the distribution function of S. We would look at computing the mean, which is the average claims, the variance, the various moments for it. So this is what typically we are interested in going forward. And when we are looking at the simple distribution function, if I look at a function, let's say g of x, which clearly specifies the probability that s is less than or equal to x. So this is what we are calling it as a distribution function. And if we look at it slightly closely, I can combine this with n in such a way that I'll say probability of s less than or equal to x and n equal to 0 means no claims, or probability of s less than or equal to x and n equal to 1, which means one claim. Probability of s less than or equal to x and n equal to 2, two claims, but the total claim amount is less than or equal to x. Similarly, probability of s less than or equal to x and n equal to some r claim. Now what we could see is only one of these is bound to occur. They are all mutually exclusive as well as exhaustive. So which means I could have very well written that as the overall, the summation in terms of n equal to 0 to infinite, probability of s less than or equal to x and n equal to n. So this is what is directly coming out as the probability, and on the other side I could very well write joint probability P of AB. I could very well write it as P of A times P of B given A. The same thing I will apply here. I'll say n equal to 0 to infinite, probability of n equal to n times probability of s less than or equal to x given n equal to n. Now, this is what is the distribution if we are looking at. Now this is for each individual, right? Now for the distribution of sum of independent random variables, we can very well find using the mechanism of convolutions. If we remember, our S is nothing but x1 plus x2 plus so on xn. So it's basically the sum of independent random variables. And if at all I am interested in finding out the distribution of sum of independent random variables, we can very well apply the mechanism of convolutions and try to find it out. Probably if something like z equal to x plus y kind of a form is there, where x is an independent random variable and y is an independent random variable, and if I know that f of x and f of y are their corresponding probability density functions, then we can very comfortably write f of z is nothing but f of x times f of y. right? So this is, and this can very well be written as f of x times, in case of f of y, I'll write it as f of z minus x. So this is one way we can very well go ahead, and in case of convolution I can do a summation for the across all the values of x, and in case of continuous I'll do an integration for over all the values of x, which means f of z directly comes out to me as the summation over all the x, f of x times capital F of z minus x. So this is what is going to come out as a part of the convolution. So when simplifying this, whenever we are talking of the probability that s less than or equal to x given n equal to n, this comes out as an n-fold convolution. The n-fold convolution of x means it comes out as f of x times f of x times f of x. Like that I'm getting n times, right? The convolution of each one. So for each of the variable n times I'm getting this as a n-fold convolution. So f of x times f of x times f of x is what we are typically getting. So which means now if I'm looking at the distribution function probability of s less than or equal to x, all I am saying is sigma from n equal to 0 to infinite, probability that n equal to n and n times convolution of f of x, right? So this is one simple way that we can look at. Now the most important thing that we are interested in looking at for the various compound distributions. All these are compound distributions because we are having two different distributions here. One, the random variable of number of claims, and another random variable is the claim amount itself. How do I typically compute the different movements of these compound distributions? Right? And we know a few important results in this context. Expected value of S if I want. All I am looking at is expected value of S given N. Now, we know that expected value of S given N equal to N. Right? Given that there is a fixed quantity N, what is the expected value of this? It's a simple average, right? Which is nothing but the expected value of xi over the summation of I equal to 1 to n. Now, if I assume the moments m1, m2, m3, if I am assuming the moments, if I am calling the different moments as m1, m2, m3. Now over this n, what is the expected value of xi, the first order movement? Let's say m1. Now over n we have this. So this becomes, the expected value is becoming n m1, right? So the expected value of s now, forget about n equal to n. Now if I am taking expected value of s, it is becoming expected value of n m1, which is also coming out as expected value of n times m1. So what is clearly coming out is the expected aggregate claim amount is the product of the expected individual claim amount. For the individual claim amounts, we got it as the first movement, which is m1, multiplied by the expected value of the total number of claims. So this is what is coming out as the mean of the aggregate claim amount. Now similarly, in that case, if I am interested in computing the variance of S, We know that from a compound distribution formula, we will write this as expected value of variance of S given n plus variance of expected value of S given n. Now we have already got expected value of S given n, right? We have got it as expected value of S given n. We have got it as nm1, right? So this part I can always keep it as variance of nm1, and probably this gets simplified as variance of n times m1 squared, because m1 is a constant out here. Now, how do I look at expected value of variance of S given n? The same way, if I look at variance of S given n equal to n, right? Now, ignore that n, now assume that n is fixed. What is the variance of all those elements? It's as good as the variance of all that summation itself, right? Variance of from I equal to 1 to n xi. That is what is when n equal n is n that is given. So it's as good as I take the this one out, I take the summation out and I say variance of xi. And if it is variance of xi over n, I'll take it as n times. What is the variance of xi? Where expectation of x squared minus expectation of x whole squared. Expectation of x squared is the second moment, m2, minus m1 squared. So this I can very well write it as m2 minus m1 squared. So obviously now this is becoming, now this entire thing is becoming variance of S. If I go back and write it, it is becoming expected value of n times m2 minus m1 squared plus variance of n times m1 squared. Now this I can very well take it out, expected value of n times n, expected value of n times m2 minus m1 squared plus m1 squared times variance of n. So this becomes the value for the variance of S. And of course, it's not a straightforward interpretation like your mean. In case of mean, we were able to say that the expected value of the aggregate claim amount is nothing but the expected value of number of claims multiplied by the expected value of individual claim amount. But here we could not come out with that kind of a straightforward interpretation. But still, this forms to be the variance of the aggregate claim amount. Now, one more thing which we can discuss in this context is the moment generating functions, because I may be interested in the third moment, fourth moment also. So from that perspective, first of all, just going with a moment generating function for S, we can very well write it as the expected value of e power ts, right? Now, this also I can very well write like expected value of S. I have written it as expected value of S given n. The same logic if I am putting here expected value of e power ts given n. I can write it like this. Now, if I go a little bit more, now let me take the expected value of e power ts given n equal to n. Right now, if I am looking at for a fixed n, it becomes expected value of e to the power of tx1 plus tx2 plus so on txn. Now I could very well, now we know that x1, x2, x3 are all independent. So I could very well write this entire stuff. I could very well write this entire stuff as expected value of e power txi and an individual multiplication of each one of them. Can I do that? Because at the end, it is the multiplication of all of them that is coming out to this value. And each one is identically distributed also. Now, because each xi's are identically distributed, the MGF, the moment generating function for them, should be the same. So, mx of t should be the same, which means this entire thing can get boiled down to expected value of this entire thing, expected value of e power, this is nothing but the moment generating function of t of each xi. But of course, because they are identical, the moment generating function will be the same. So I am taking it as generalized as x. So which is nothing but this is the once I have the moment generating function for one of them, I am taking it as to the power n. So now if you look at this internal part, expected value of e power ts, expected value of e power ts given n, it is nothing but mxt to the power n. And now if I really want mst, right, but I want mst, which is nothing but expected value of e power ts, expected value of mxt to the power n, right? Expected value of mxt to the power n is what is coming out as mst. So my mst, just a little bit of workout here. We know that mst we have just now derived that it is expected value of mxt to the power n. Now all I'll write this is expected value of e to the power of log mxt to the power n. I can write it because at the end it is coming out to be the same. E to the power of log something to the base e is coming out to mxt to the power of n itself. So in a way, it is very much coming out. Now I can very well bring the logarithm in between. So expected value of e to the power of n times log mx of t. Now I could very well bring out e to the power expected value of e to the power of n. I could very comfortably get out, which becomes mn. Mn of log mx of t. So this is what will become my moment generating function of s. Mn times log mx of t will directly become my moment generating function for the aggregate class. So it is expressed in terms of moment generating function of n as well as the moment generating function of s. But here also we did not specify any kind of distributions for n or x, right? So using these, now let's try to get into a different kinds of distributions And based on these distributions, we can see how we can, if I am assuming that the losses are going to follow, let's say, a Poisson distribution, or losses are going to follow a binomial. So here we are going to look at three such kind of distribution. One following a Poisson distribution. Let's again try computing what are the mean, the variance, the various movements, etc. Similarly, when I look at a binomial distribution, again a similar kind of calculation, and we also will talk about a negative binomial kind of a distribution. So all these ones, how well they are going to impact us, how well we are going to compute the various results from them is something which we are going to look at. Okay, now let's go ahead first with a compound Poisson distribution. The compound distribution is Poisson. Now aggregate claims, where I am looking at the number of claims, is going to follow a Poisson distribution. If I know that the number of claims is going to follow a Poisson distribution with mean lambda, and in that case, we say that S, which is an aggregate claims, is following a compound Poisson distribution. If N is following a Poisson distribution with a mean lambda, then we say that S is following a compound Poisson distribution with a parameter lambda, right? And we can very well take f of x as the distribution function of the individual claim amount. Now from here, because N is following a Poisson distribution, a few calculations are ready-made for us. Expected value of N is lambda. The variance of N is lambda. Right from the Poisson distribution I am directly using. The moment generating function of N is again the moment generating function of the Poisson distribution, which is e to the power of lambda times e power t minus 1. Now, based on these numbers, I am really interested in finding out the expected value of S. Now we know expected value of S is nothing but expected value of N times M1. Now which is lambda N1 over. Similarly, if I want the variance of S, we have got the variance of S earlier as what is the formula we have got? Expected value of N times M2 minus M1 squared plus variance of N times M1 squared, right? So you could very comfortably write expected value of N is lambda. Lambda M2 minus lambda M1 squared plus variance of N is still lambda plus lambda M1 squared goes off and I get lambda M2. Similarly, I can try finding out the moment generating function of S. What is the moment generating function? Okay, we have written it as Mn, right? What is the moment generating function? We have written it as Mn of log mx of t. Now, what is the Mn's moment generating? N's moment generating function e to the power of lambda times e to the power of t, e to the power of log mx of t, which becomes mxt minus 1. So this becomes the moment generating function of S, right? Mst will become e to the power of lambda mxt minus 1. Now, the mean, variance, they are expressed in a very simplistic form. And we could also look at even a further more classifications or computations also if possible. using this distribution. Even it comes out that the skewness for this skewness of S comes out very simple as lambda M3. Right? For that, probably now that I know, we can use actually a cumulant generating function, which is nothing but the logarithm of the moment generating function, right? And I can differentiate the CGF, right? We can very well take the CGF. We can differentiate the CGF twice, or if I'm generating, if I'm see, once I have created a moment generating function, and I am taking the first derivative of the CGF at t equal to 0. I get the first moment, which is the mean, first central moment. Then again, second derivative at 0, I get it as the variance. And the third derivative at 0, I get it as the skewness. So the same logic, if I really want, I get a cumulative generating function log MST, and I have to differentiate it 3 times. I have to differentiate it 3 times at t equal to 0, and I can very well find out. So log MST, so we know that right now MST is nothing but e to the power of lambda times mxt minus 1. Lambda times mxt minus 1. So what I can very well do, log mst is my cumulant generating function, which is lambda times mx of t minus 1. Now if you see, if I have to differentiate this, right, I have to differentiate it 3 times. Okay, d by dt of log mst, if I want, it is nothing but lambda times d by dt of mxt. That's it. Now the same logic, d by dt squared, d squared by dt squared log mst is again lambda times d squared by dt squared mxt, and similarly d cube by dt cube mxt, right, which directly comes, this is d cube by dt cube is not mxt at t equal to 0. At t equal to 0, this is nothing but this is I mean, when I'm differentiating the mxt, this is m3. So it is becoming lambda m3. The central moment at t equal to 0 is directly becoming lambda m3. And the coefficient of skewness, I can directly take it as the skewness divided by the variance. Variance is lambda m2 to the power 3 by 2. So this is how we are able to compute the skewness, the mean, the variance, and even the moment generating function, if at all our number of claims is following a kind of a Poisson distribution. And here it is coming out that S is positively skewed, and because M3 is the third moment above 0. And so this is clearly saying that even if xi's are negatively skewed, the distribution of S is positively skewed, right? So this is how in case our number of number of claims is following a Poisson distribution, These are what are the numbers that we can very well get into. Similarly, think of if the number of claims, if the number of claims follow a binomial distribution, then the aggregate claims we say S. S is going to follow a compound binomial distribution. Right? If at all I am using a binomial distribution for N, then for S we are calling it as a compound binomial. Especially let's say for a group life insurance policy where they are covering N lives and each life is independent. So if I am more interested in finding out the distribution of the number of deaths in a year, we can very well assume that to be a binomial. So in that case, it so happens that the expected value of n for a binomial distribution, we know that the mean is np, variance of n, which comes out as np into 1 minus p, and the moment generating function of n is nothing but p e power p plus 1 minus p to the power n. Now the same logic, n is having a binomial distribution, which means s is having a compound binomial distribution. But the only thing in this case compared to a Poisson distribution is there is an upper limit to the number of claims, whereas in Poisson literally there is no upper limit to the number of claims. Now using this data, if I want to find out the expected value of S, it becomes NPM1. But the variance of S slightly we have to work out for the variance of S, because it comes out as the expected value of N, which is NP times M2 minus M1 squared plus variance of N, NP into 1 minus P times M1 squared. So on a simplification, it becomes NPM2 minus NPM1 squared plus NPM1 squared minus NP squared M1 squared. So this is going off. So it becomes NPM2 minus NP squared M1 squared. This becomes the variance of S. Similarly, now that I know that the moment generating function of N is p e power p plus 1 minus p to the power n, I am more interested in the moment generating function of S, which we know that it comes out as mn times log mn of log mx of t. Mn log mx of t. This is what is the moment generating function of S. So here I could very well write it as p e to the power of log mx t plus 1 minus p to the power n, which works out as, this will work out as p mxt plus 1 minus p to the power n. Right? This becomes my MST. Now the same logic, probably even if I want to go for a third central moment, which is for the skewness, I could very well take log MST, right? I could very well from the cumulant generating function. The cumulant generating function for us is directly coming out as log mx of t. Now the same thing for this, if I am more interested, right? Now I can very well for the mx of t or for ms of t, I am looking at the cumulant generating function. So I'm looking at log ms of t, which is nothing but the logarithm of this entire stuff, log p mx t plus 1 minus p to the power n. That is what is becoming log mst, or probably it is n times log p mxt plus 1 minus p. Now this I want to differentiate it 3 times. So the first differentiation will give me n divided by, log of this. So the log of this is going to give me p mx of t plus 1 minus p, and the derivative of this is nothing but d by dt of mx of t, p mx of t. So np by p mx of t plus 1 minus p and d by dt of mx of t. Now the same logic, probably if I keep continuing, right, if I keep continuing in each of the layers, it's very comfortably working out for me that I do a differentiation of it twice. Now let's do it. Log mst is equal to n log mx p mxt plus 1 minus p, right? Now let me talk about d by dt of log mst, the first derivative of this. Okay, so this is my variable. So it becomes n by p mxt plus 1 minus p, and the derivative of the inside stuff is nothing but p times d by dt mxt, right? Now the same thing, if I have to do a differentiation once again, log mst for the second time, okay, this is of the division form, so probably I'll write it as p mxt plus 1 minus p times whatever is the derivative of the numerator, np times d squared by dt squared mxt minus np d by dt mxt times the derivative of the denominator, which becomes p times d by dt of mxt divided by p mxt plus 1 minus p. Now this becomes my second derivative. And if I am going ahead with this simplification again, when I am looking at d cube by dt cube log mst, I can very well simplify. Now this and this, only the first part of this, p mxt times, I can look at it as p mxt times np d cube by dt cube mxt plus np d squared by dt squared mxt times whatever is the derivative p d by dt of mxt. So if I'm going like this, taking the third derivative, and finally we have to understand when I'm substituting t equal to 0, mx is becoming my mean. So mx of 0 is directly becoming my, when I'm substituting a 0 in all these things, overall it is coming out as np times d cube by dt cube mxt plus pmx divided by pmxt plus q, and similarly I'm getting some np squared. So whatever is getting simplified, overall it is working out that the skewness is nothing but np m3 minus 3 np squared m2 m1 plus 2 np cube m1 cube. You can try simplifying all these things by substituting n equal to 0. This is what will come to us as the value of the skewness divided by the variance to the power 3 by 2 will give me the coefficient of skewness. Now the same logic I can very well follow if my n is following a negative binomial. In that case, my s is following a compound negative binomial kind of a distribution. We have to understand only the conceptual part behind it. Now, if n is following the negative binomial distribution, we know that the density function, or we know that the probability function is k plus n minus 1 cn p power k q power n. This is what is our negative binomial type 2 kind of a distribution. And we know that the expected value of n becomes kq by p. Variance of n in this case will become kq by p squared, and the moment generating function of n will become p power k times 1 minus q e power t to the power minus k. So these are the typical values that are associated with a negative binomial kind of a distribution. In some cases, this is much more better compared to a Poisson. Especially in case of Poisson, we see that the variance is same as the mean, which is lambda. Whereas here, the variance is greater than the mean. So wherever we have a real world situation where the variance is exceeding the mean heavily, probably the better choice is a negative binomial rather than a Poisson distribution, right? So generally, whenever in a sample we see that the variance is excess of the mean, probably a compound negative binomial is what will become handy for us. Now again, using this, if I am more interested in finding out the expected value of S, it is nothing but kq by p times m1. The variance of S, again we can simplify for the same, it becomes kq by p times m2 plus kq squared by p squared times m1 squared. And the same way, if I am going with ms of t, it becomes p power k divided by 1 minus q mxt to the power k. All these things can very well be simplified, and the same way going ahead with the third derivative of the cumulant generating function will give us the coefficient of skewness also. So this kind of understanding for various compound distributions where the number or where the frequency is following either a Poisson or a binomial or a negative binomial kind of distribution, and the aggregate claim amount is expected to follow a kind of a compound distribution wherein by knowing the mean, variance, moment generating functions of our individual claim frequency distributions, we can try finding out the moment generating functions, mean, variance, distribution for our aggregate claim distributions as well. All right.